The paper discusses the extraction of sea ice via remote sensing imagery, focusing on algorithms, datasets, applications, and challenges. It provides a comprehensive review of recent advancements in this field, particularly emphasizing deep learning-based approaches over the past 5 years. Sea ice extraction is crucial for various applications such as polar navigation, terrain analysis, and polar expedition. The paper highlights that machine learning methods have significantly contributed to the field of SIE, with a focus on active microwave remote sensing technologies, notably SAR, which offers higher resolution capabilities suitable for fine-scale sea ice mapping. The paper categorizes SI methods into 3 groups: classical image segmentation approach, machine learning-based approach, and deep learning-based methods. Classical image segmentation methods rely on statistical algorithms that combine probabilistic models and classical classification methods with texture or polarization features to generate sea ice type maps. Recent publications include the use of a new Bayesian risk function to minimize the likelihood ratio for polarimetric SAR data supervised classification, achieving a sea ice classification accuracy of 99.9%. Other classical methods utilize Bayesian theorem to compute the posterior probabilities of each class at each observed location based on the texture features extracted from the gray-level CO occurrence matrix of the image. Machine learning-based methods, on the other hand, involve the use of labels to classify each pixel in the SAR imagery as ice or water. The estimated ice concentration is then obtained by incorporating the labeled data into the Bayesian framework. Deep learning-based methods, as a branch of machine learning, have attracted more attention in the last 5 years. These methods convert the SI problem to another common topic, namely the semantic segmentation problem, which determines the category of each pixel via a post-classification procedure after the category probability is regressed by the deep convolutional neural networks. The paper also reviews the accessible ICE datasets, including SAR-based datasets, the optical-based datasets, and others. It outlines downstream tasks and enumerates the generated geospatial information products resulting from ICE extraction, such as climate research, navigation, geographic information systems, GIS, production, and others. Finally, the paper highlights areas where future developments are needed, providing insightful observations and inspiring future research directions. This section of the research paper discusses various methodologies employed in sea ice classification, including classical image segmentation methods and machine learning-based approaches. Classical methods, such as thresholding and edge detection, are effective for simple segmentation tasks but struggle with complex scenes and sensitivity to image brightness and noise. To overcome these limitations, researchers have turned to advanced techniques like machine learning, which leverages the polarimetric characteristics of sea ice images and integrates spatial context and texture features for enhanced accuracy. One prominent machine learning method is the iterative region growing using semantics, IRGS, algorithm, which models backscatter characteristics using Gaussian statistics and incorporates a Markov random field model to capture spatial relationships. This unsupervised classification algorithm assigns arbitrary class labels to identified regions, requiring manual intervention to map these labels to actual classes. Several studies have built upon IRGS, combining it with other classification methodologies to improve performance and accuracy in sea ice analysis. Another significant method is the random forest (RF) classifier, which has been applied in various contexts of sea ice analysis, including sea ice mapping, classification of different ice types, feature selection, noise correction, and automated ice detection. RF models have shown effectiveness in leveraging various image features for accurate and robust classification results. These researches demonstrate the versatility of IRGS and RF, as well as their integration with different classification methodologies, leading to improved performance and enhanced classification accuracy in sea ice analysis. The paper also highlights the limitations of classical image segmentation methods, paving the way for exploring alternative approaches to address the challenges associated with threshold-based segmentation. The pages discuss the application of machine learning and deep learning techniques in sea ice classification. Various algorithms such as multi-layer perceptron, MLP, support vector machine, SVM, decision tree, DT, and random forest, RF, have been used for sea ice classification. MLP has been shown to be particularly effective, providing accurate classification results and enabling the estimation of sea ice parameters. SVMs, although less popular now, offer robustness and suitability for binary classification tasks. Other methods like LR, K-means, and DT have also been employed with varying degrees of success. Deep learning methods, such as CNNs, have recently gained popularity due to their ability to automatically learn and extract features, leading to improved accuracy in sea ice classification. The use of CNNs has been demonstrated in various studies, showcasing their effectiveness in feature extraction and classification, particularly in complex scenarios. Overall, the integration of machine learning and deep learning techniques has significantly improved the accuracy and efficiency of sea ice classification, contributing to advancements in sea ice research and monitoring. The research on deep learning for sea ice extraction, SAI, has made significant advancements in recent years. Various deep learning architectures have been applied to classify sea ice from various data sources, achieving accurate results. The use of transfer learning, data augmentation, and input size has been investigated, showcasing the effectiveness of dense net and UNet models. The application of long short-term memory, LSTM, networks has also improved the accuracy of sea ice classification, considering spatial characteristics and temporal variations. Semi-supervised learning techniques have been introduced to better utilize in-labeled data, enhancing model performance. Unsupervised learning approaches, leveraging the electromagnetic properties of sea ice in SAR imagery, have also been explored. These advancements demonstrate the potential of deep learning inside tasks, contributing to the development of more accurate and robust models for sea ice classification and estimation. Here is a combined summary of pages 9 and 10 of the research paper. The application of deep learning in sea ice classification has shown promising results, but it is limited by the scarcity of labeled sea ice data. To address this issue, researchers have proposed physics-guided learning approaches that leverage physical models and prior knowledge to improve the interpretability and generalization capability of deep learning models. By encoding physical attributes into the learning process, these approaches can achieve comparable results to supervised CNN learning methods with limited labeled data. One of the major limitations of deep learning in sea ice classification is the lack of large-scale and representative benchmark datasets. To address this limitation, researchers have compiled a comprehensive database of openly accessible sea ice datasets, including SAR-based, optical-based, airborne camera-based, and drone-based datasets. This database provides a standardized framework for future research and enables the evaluation of different sea ice classification methods. SAR-based datasets are widely used for sea ice classification due to their ability to capture the radiation characteristics of sea ice. The radar wavelength, polarization mode, and incidence angle of SAR have significant impacts on the extraction performance. For instance, X-band and Q-band SAR are suitable for winter sea ice monitoring, while L-band offers advantages for summer sea ice monitoring. Polarimetric techniques can provide valuable insights for sea ice identification by capturing detailed surface information using polarimetric SAR. The compiled database includes 12 datasets, including SIST-SAR7, 10 GOP-SAR-WV, SAR-WV semantic segmentation, CO-VMRML, SAR-based ice types, ice edge dataset, AI4 sea ice, and Arctic sea ice cover product based on SAR. These datasets provide a diverse range of ice categories and labels, enabling the evaluation of different sea ice classification methods. In addition to SAR-based datasets, the database also includes optical-based datasets, such as MODIS, VIIRS, Landsat series, Sentinel series, and HY1. These datasets provide valuable information about ice characteristics such as color, texture, and spectral properties, which can be used for ice classification and monitoring. Overall, the compiled database provides a comprehensive resource for the research community, enabling the evaluation and development of new sea ice classification methods. Here is a combined summary of pages 11 and 12. The authors discuss the importance of optical and alternative acquisition methods for ice classification datasets. Optical sensors, such as the SCA sensor, capture spectral information or radiation characteristics in different bands, enabling the acquisition of valuable data on ice morphology, types, and distribution. These sensors are widely employed in remote sensing and Earth observation, providing valuable data for ice monitoring and research purposes. There are currently 2 open-source optical imagery datasets available. The 2021 GAOFED dataset, which consists of high-1 visible light images with a resolution of 50 meters, and the Arctic Sea Ice Image Masking dataset, which comprises 3,392 satellite images of the Hudson Bay sea ice in the Canadian Arctic region. Additionally, the authors mention alternative acquisition methods, including airborne camera-based datasets, such as the dataset constructed from GoPro images captured during a 2-month expedition in the Ross Sea, Antarctica, and drone-based datasets, such as the River Ice Segmentation dataset and the NWPUYRCC2 dataset. The authors highlight the importance of accurate spatial distribution and dynamic changes of sea ice, which has become increasingly vital in various domains, including weather forecasting, maritime safety, resource development, and ecological conservation. They discuss the applications of sea ice classification in meteorological forecasting and climate research, where the extraction and classification of sea ice data can improve the predictive capabilities of climate models and enhance our understanding of sea ice response to climate change. Furthermore, the authors emphasize the significance of sea ice observation data in monitoring climate change, as sea ice serves as a crucial indicator of climate change. Regular extraction and classification of sea ice can monitor its temporal and spatial variations, analyze the trends of sea ice retreat and formation, and provide data support for climate change research. Additionally, the authors discuss the importance of accurate extraction and classification of sea ice data in maritime and ocean navigation, enabling the efficient generation of valuable geographic information products. The Arctic Northeast Passage, NEP, has undergone significant changes in sea ice conditions, impacting both the environment and navigational capabilities. Research indicates a continued reduction in Arctic sea ice, leading to the shortening of trade routes and potentially affecting the global economy. The extent and thickness of sea ice hold significant importance for navigation, as emphasized in recent studies. Novel research has focused on enhancing the spatial and temporal resolution of sea ice monitoring to accurately evaluate the navigational capabilities of critical straits and regions. Geographic information products, such as sea ice distribution maps, ice edge charts, and route planning tools, serve as crucial aids for ships, enabling them to navigate safely and avoid ice-prone areas. The integration of remote sensing techniques has led to significant advancements in generating geographic information products related to ice and polar regions. Platforms like Quantarctica, Arctic Web, and Sea Ice Index provide valuable resources for researchers, scientists, and policymakers working in the polar regions. These systems collectively contribute to a comprehensive understanding of the polar regions and their dynamic characteristics, supporting various applications in polar environments. The detection of sea ice is a crucial task for understanding the marine environment and its impact on climate change. However, this task faces several challenges, including limited data availability, difficulties in detecting underwater ice, and the complexity of sea ice features. To address these issues, researchers have proposed various methods, such as multi-sensor integration and unsupervised deep learning. Multi-sensor integration combines different technological approaches, including microwave radar, optical sensors, and acoustic techniques, to obtain comprehensive information about sea ice. This method has been demonstrated in the classification of sea ice using SAR and optical images. For instance, by replacing the B band in RGB images with a single SAR band, superior results were achieved due to the weaker texture characteristics of the B band and the better reflection properties of SAR for sea ice. Furthermore, concatenating a single SAR band with the RGB 3-channel image forms a 4-channel image, enhancing the model's performance in sea ice classification tasks. Unsupervised deep learning emerges as a promising avenue to address the scarcity of annotated datasets in sea ice research. This approach leverages intrinsic structures and patterns within sea ice imagery, enabling the automatic extraction of informative features without relying on external labels or manual feature engineering. Techniques like autoencoders, GANs, and VAEs are effective in acquiring meaningful representations from unlabeled sea ice data, discovering similarities, textures, shapes, and other discernible patterns inherent in sea ice images. These representations can then be transformed into valuable feature representations, enhancing the generalizability and robustness of sea ice classification models across varying timeframes, locations, and sensor conditions. However, the application of unsupervised deep learning methods to SIG tasks introduces certain challenges. The absence of external labels as supervision signals may yield inaccurate or ambiguous feature representations. It is therefore essential to design suitable objective functions and loss functions to guide the unsupervised learning process, ensuring the acquired features effectively facilitate the classification and analysis of sea ice images. Additionally, training unsupervised learning models may necessitate increased computational resources and time due to the involvement of complex network architectures and larger-scale datasets. Evaluating the performance of unsupervised learning methods and conducting comparative analyses to discern the strengths and weaknesses of different approaches represent inherently challenging tasks in this domain. In conclusion, the integration of multi-sensor data and the application of unsupervised deep learning techniques offer promising solutions to the challenges faced in sea ice detection. These approaches can provide more comprehensive and accurate data support for sea ice research and related applications. The authors present a comprehensive approach to sea ice image segmentation and cartographic applications. The Segmentation-Aware Module, SAM, demonstrates high precision in distinguishing different types of sea ice, but lacks the capability to associate segmentation results with predefined sea ice categories. To address this, the authors introduce the CLIP model as an auxiliary classifier, which establishes the connection between image content and category names, enabling accurate classification of sea ice image patches into their respective categories. In the context of cartographic applications, researchers have developed various polar geographic information systems, GIS, tailored for polar regions, supporting the processing, analysis, and visualization of polar environments and related data. However, these systems have limited integration of information and analysis paths, resulting in somewhat idealized outcomes. To improve these systems, the authors suggest feature enhancements and architectural directions, including data integration and management, structured modeling, and geospatial analysis capabilities. The authors also highlight the importance of real-time data and updates, as well as the potential benefits of incorporating technologies such as distributed computing, cloud computing, and artificial intelligence to enhance system performance and scalability. Furthermore, the authors discuss the challenges of polar map projections, including severe distortion of commonly used projection methods and the difficulty of finding a suitable balance between equal area and equal angle properties. They highlight the need for novel polar projection methods, exploring new mathematical models or adopting technologies like machine learning and artificial intelligence to achieve more accurate and geographically realistic polar projections. In terms of future directions, the authors suggest that researchers can continue to explore and develop new polar projection methods, improve data sharing, standardization, and interoperability, and enhance the overall performance and practicality of polar systems. This will facilitate comprehensive support for scientific research, navigation safety, and environmental protection. The research paper discusses various methods used for sea ice detection and classification, focusing on the use of synthetic aperture radar, SAR, data. It highlights the importance of multi-scale and multi-resolution polar projections for effective mapping of polar regions, including local glaciers and the entire polar region. The paper also emphasizes the need for dynamic polar projections that can adapt to changes in the geographical environment, such as sea ice melting and glacier movements. Additionally, it explores the application of multidimensional polar projections to process and present data involving spatial dimensions, time, temperature, and thickness. The authors identify potential research directions based on the challenges encountered in detection methods, model approaches, and cartographic applications. The paper provides a comprehensive overview of the current methods used for sea ice segmentation and classification, including classical image segmentation methods, machine learning-based methods, and deep learning-based methods. It also discusses the limitations and assumptions of these methods and highlights the importance of future work in this field. This study focuses on the classification and estimation of sea ice concentration using various remote sensing satellite images and deep learning models. It provides an overview of numerous research papers that employ different methodologies and algorithms to identify and quantify sea ice. The papers reviewed utilize a range of techniques, including support vector machines, convolutional neural networks, and conditional random fields, to classify sea ice and open water from synthetic aperture radar (SAR) imagery. These methods are applied to various regions, such as the Arctic, Antarctica, and the Baltic Sea, demonstrating their adaptability across different geographical locations. The research highlights the importance of accurately identifying and quantifying sea ice for environmental monitoring, climate change studies, and navigation safety. The use of deep learning models, particularly convolutional neural networks, has shown promising results in improving the accuracy of sea ice classification and concentration estimation. These models can be trained on labeled datasets and fine-tuned for specific regions and ice conditions, enhancing their performance over traditional methods. Moreover, the study emphasizes the role of feature extraction and selection in improving the accuracy of sea ice classification. Techniques such as spatial and temporal feature extraction, spectral spatial joint features, and multiscale semantic features are discussed. These features can be combined with various deep learning architectures, such as the UNet, Deep Lab, and ResNet, to achieve better results in identifying different types of sea ice and distinguishing them from open water. The research also touches upon the issue of label errors in training datasets and their impact on model performance. It discusses strategies for mitigating these errors, including the use of aleatoric uncertainties and end-to-end Resunnekref models. Additionally, the study highlights the potential for integrating data from multiple sensors, such as SAR and passive microwave sensors, to enhance the reliability of sea ice classification and concentration estimation. In conclusion, the reviewed papers demonstrate the significant advancements made in sea ice classification and concentration estimation using deep learning models and remote sensing data. The research emphasizes the importance of feature extraction, model selection, and error mitigation in achieving accurate results. It also underscores the potential for integrating data from various sensors to improve the reliability of sea ice monitoring. This research paper presents a comprehensive review of various studies related to sea ice concentration prediction, classification, and mapping. The authors have compiled an extensive list of references, covering topics such as deep learning technology, unsupervised and semi-supervised methods, synthetic aperture radar, SAR, images, and sea ice change detection. Several studies have employed deep learning techniques for sea ice classification, including the use of convolutional neural networks, CNNs, and generative adversarial networks, GANs. These approaches have shown promising results in improving the accuracy of sea ice classification. Additionally, researchers have explored the application of transfer learning and domain adaptation to enhance the performance of sea ice classification models. The paper also reviews various studies on sea ice concentration prediction, including the use of machine learning algorithms and physical models. These approaches aim to improve the accuracy of sea ice concentration predictions, which is crucial for climate modeling, navigation, and environmental monitoring. Furthermore, the authors discuss the importance of mapping and projecting sea ice data, highlighting the challenges and limitations of existing methods. They review various projections and transformations used in sea ice mapping, including the Gauss projection, mnemonic projection, and others. The paper also touches on the topic of oil behavior in sea ice, highlighting the potential environmental impacts of oil spills in Arctic regions. Moreover, it discusses the effects of sea ice loss on global ocean circulations and interbasin ocean heat exchanges. Finally, the authors review various studies on the impact of sea ice retreat on marine aerosol emissions, Indian Ocean swells, and other environmental phenomena. They also discuss the application of joint semantic segmentation frameworks for land use classification, collaborative attention-based heterogeneous gated fusion networks, and mutually guided contexts for sea ice classification. Overall, this paper provides a comprehensive review of the current state of research in sea ice concentration prediction, classification, and mapping, highlighting the importance of these topics for climate modeling, environmental monitoring, and navigation.